Hello again, Mr. Schlesser from the Quantitative Reasoning Center. This is a carburetor off of an XR200 Honda. Now, when you build a carburetor, it's very important to be able to accurately calculate the volume of the air that's flowing through the thing. Okay, you have to accurately calculate that so that you can properly create the Venturi effect, which pulls the fuel up through there, mixes it with the air so it can be burned by the cylinder. Now, whether you're messing around with a motorcycle carburetor or maybe this bad boy, this tricked out Holley 4-barrel double pumper off my Camaro, whoa, 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 more power, you're going to need to know how to calculate volume very accurately. Okay, so let's do something along those lines. Today we're going to calculate the volume of an object, and the object we have is a solid which has a triangular cross-section and a length of 8 centimeters. Now, I know that if you have a 6th grade education, you could probably calculate the volume of this thing without too much trouble. But sometimes we take something that's simple and apply a principle to it so that we can apply it later once things get a little harder. So the object of today is not to find the volume of this thing per se, although we will. The object is to learn a technique of calculating the volume. Okay, you with me? Alright, well, let's do it. For part A, they ask us to slice this thing up in this direction. Okay, we'll call this X, and so this direction is X. So we're going to make little slices like so. We're going to make let's just make a typical slice out of that thing. Okay, and if we pull that slice out, it's going to look something like this. Of course, that's a right angle. Okay, and it's going to have a depth, and so that is just a typical slice that we pulled out of that thing. And since this is our X direction, we can call its depth or width delta X. Okay, now we know the height of this thing is 7. The width across here is, of course, 4, and the units are centimeters. We'll add that later. Okay, so now if I wanted to calculate just the volume of this little slice that I've pulled out, you could do it quite simply. Area of a triangle, 1/2 base times height. So you have 1/2 base times height, 7. Okay, that is the area of the triangle face. And now this thing has depth, and that depth, of course, is delta X. So we'll call that delta X. So now we have the volume of one sample cross-section that we've pulled out of our big object. Okay, so we can calculate this. Of course, it's 14 delta X. Now you probably notice my numbers are a little different than yours for 8.1 number 26, so that you get the benefit of working it on your own. Principles are all the same. Okay, so we have the volume of a sample triangle that we've pulled out of there. Okay, now you'll notice that we've just got one of these. Now we're going to need to add up a whole bunch of these, and we're going to, in fact, we're going to add up not only all of them that are delta X wide, we're going to take the limit as X goes to 0, and then we're going to calculate the entire volume in this method. Okay, so let's start out here with just our friend the sigma, and we're going to add up all these little triangular pieces, and they are, of course, they're all the same volume, 14 delta X. Okay, and that is just the summation of all of our sample triangles. Now, like I said, we want to make delta X as small as we can. In fact, we're going to take the limit as delta X approaches 0. So now we can get a very accurate estimate of that. And this may look familiar to you as the integral notation that we've used prior. Okay, so let's go ahead and write that as an integral, shall we? That the integral of 14, and now delta x, you may know it better as dx. Okay, now let's look at our triangle. We've got these slices, right? And we're going to go from here, our starting point, up to here, our end point. So I'm going from 0 to 8, because this is 8 centimeters in length, okay? So we're going from 0 to 8. Now this is a pretty simple integral. You can play along at home. You'll see that it is 14x evaluated from 0 to 8. And we all know the fundamental theorem of calculus. We can apply it here. So I have 14 times 8 minus 14 times 0. And that will give us our volume, which is, of course, 112 cubic centimeters. Okay, gosh, that was fun, but there's more. Let's chop this thing up in a different way, shall we? Alrighty, I've got the board all cleaned off again. Now, instead of slicing it in this manner, we're going to take a slice in another direction. We're going to slice this thing across here and in this fashion. So if we slice this thing in this manner, the shape of the pieces that we're going to pull out of here are, of course, rectangles. So we're going to pull rectangles out of here, and we're going to do the same thing we did last time. We're going to add up the volume of all those rectangles we pull out of there, and putting them all together, that'll give us the volume of the entire object. This one's a little more tricky though, because as you'll notice, the width of my rectangles is decreasing as I approach the bottom of this 7 centimeter height here. So up here at the top it starts out at 4, but as I work my way down it goes to 0. So we're going to have to account for that. We'll use a principle called similar triangles to do that. Okay, so this is a typical piece. I pulled it out of here. It is, of course, 8 centimeters this direction. It is, I'm going to call this height. We'll call this H. I actually will call this H. The length from here to here. Okay, with me on that? And so we can call the width, this width across here, we just call that width. And then we have a depth to this thing too. Whoops, how crazy there. We have a depth as well. And we're going to call that delta H. That is just this little width there, which is the depth of my rectangle. Delta H. So, let's get started, shall we? Okay, so the big problem here is I need to know W, and W is going to be changing as we talked about. Okay, we're going to use a principle called similar triangles to calculate this width. Now, the way it works is, let's just see what the end of this piece looks like here. It is 7 centimeters high. It has a width of 4 at the top, and I'm going to be dropping down H, and so this width, when I get down to here, is going to be W. Good name for width. Okay, the similar triangles principle works like this. The width is related to 4. Width is related to 4 as the height is related to 7. Now, this is the tricky part. How high am I? Well, I am 7 minus h. See that? 7 minus h. So I was 7, and I've come down h. And that's the way the similar triangles relates the height and the width. Okay, so now I have a formula that I can sort of work with here. I can solve for w. So w is equal to 7 minus h divided by 7 times 4. Let's just do a little algebra here. And I can simplify this. W equals 4 minus 4/7 h. Pretty simple algebra. I'm sure you can do that at home. Okay, now I have an equation for my width. Okay, so now I know what the width is 4 minus 4/7 h. Now I know everything I need to know in order to calculate the volume of that rectangle. So let's go ahead and do that. The volume of this rectangle is, of course, length times width times the depth, and we know that to be delta h. So we have 8 times the width, which is 4 minus 4/7 h, times delta h, the depth. Okay, and now we can again do a little algebra here and come up with some numbers here. Okay, not hard to do. Okay, so now we have an equation for the volume of one chunk. And not only that, but it's representative of any chunk I want to pull out of this object over here. Okay, and again, we're going to take all these slices and we're going to add them up. Okay, so let's go ahead and do that. We're going to take the sum of all those pieces, and not only that, we're going to take the limit as delta h approaches 0, so we can get a very accurate measurement. 32 minus 32/7h times delta h. Okay, and the limit as it goes to 0, we all know that to be an integral. So we have the integral, and we'll get to the limits of integration here in a second, of 32 minus 32/7h dh. Okay, now let's look at the limits of integration. We've sliced this thing in this manner, and we're going to go from here clear down to here. So we're going to be going from 0 to 7. Okay, so those are our limits of integration. 0 to 7. Alrighty, now let's just take this integral. Doesn't look too hard. So I'm going to have 32h minus 32/7 h squared over 2 evaluated from 0 to 7. Okay, so we can calculate that quite simply. We're going to put in 7, and then we're going to subtract off the value with 0. So let's make a little room on the board here. Let's try it right here. So let's go ahead and rewrite this function up here so we have room to work. Minus 32/7 h squared over 2 evaluated from 0 to 7. Okay, first of all we're going to throw 7 in that thing. 32 times 7 minus 32/7 times 7 squared over 2. And then we're going to subtract this whole thing, evaluated 0. Fundamental theorem of calculus. 32 times 0 minus, well, really doesn't matter because this one is 0. This is all 0, and this one comes out to 224 minus 112. You got your honor later handy. And then we come up with a grand total of 112 cubic centimeters. Okay, so we took a fairly simple object, which you could probably calculate the volume quite easily, but we did it in such a way that it's going to teach you a principle for calculating the volume of much more complicated objects in the future. So, hope you take the lesson to heart. Have a good day.